the concept that you've seen a lot of over the years, but perhaps not the way we're going to discuss it. What is a set? Well, let me ask another. What is an army? What is a bunch? What is a cadre? What is a detachment? What is an echelon? That's a fancy word. What is a flock? What is a horde? Well, I like, what is an ilk? What are these? Groups. They're groups. The more formal title for them, they are collective nouns. They are used in the singular form. I have a bunch of bananas. I have a quiver of arrows. I have a zoo of animals, or a zoo of students, depending on their behaviors. So, there are collective nouns for every letter of the alphabet. If you go out on Google, boom, there they are. Oh, I just lied. I don't like to do that. There isn't one for the letter X. But in mathematics, that's the set that we're most interested in. X is a set of unknowns. Easy enough, right? So, mathematics is made up of sets. Remember, mathematics is the search for patterns and the application thereof. So again, let's start with an easy set. The set A contains the elements A and B and C. It has 8 subsets. The subsets of A are the empty set, the set containing A, the set containing B, the set containing C, the set containing A and B, the set containing A and C, the set containing B and C, and the set containing A, B, and C. So we have sets, we have subsets. We say two sets have the same cardinality, or the same number of elements, if we can put the two sets in a one-to-one correspondence. That is, every element in set A matches exactly one element in set B, and every element in set B matches exactly one in set A. And in this particular case, there are 6 different ways to show that set A and set B are the same size, because there are 6 different one-to-one correspondences. 1, 2, 3 compared to ABC, or ACB, or BAC, or BCA, or CAB, or CBA. 1 matches the first element, 2 matches the second element, 3 matches the third element. And since this is a non-ordered set, then that matching can occur 6 different ways. Doesn't matter how many different ways it can be done. The fact is it can be matched. Okay. We also have the concept of union. And the symbol for union is a big parabola-looking U. So if I say A union B, what does that say? What is the union of two sets?
Combination? Combination or sum?
Well, I don't know if I'd go with the word combination, but it's everything is in A and everything is in B. And again, since these are not ordered sets, even though I wrote it alphabetically and increasingly here, they don't have to be written that way. So I might put A, 3, B, C, 2, 1. 1, 2, 3, 4, 5, 6. So in this case, their union has as many elements combined as A has and B has, is the sum of the elements. But if there's overlap in the set, then the overlap you don't list twice, you just do that once. We'll draw a picture of that momentarily. Well, we also have the idea of an intersection. And what is the intersection of set A and set B? If you go out here on the street, May Avenue, north-south, 74th Street, east-west, you're standing out in its intersection, what street are you standing on?
The intersection of both streets.
The intersection of both streets, okay. So the intersection, physically, is the same as the intersection. Mathematically, it's where they overlap. So where do set A and set B overlap? Intersection? Well, they overlap in the intersection. I'm saying, what elements are in that intersection?
None?
None. And what do we call the set with none in it, with nothing there?
Non-function?
We call it the empty set. Now, yeah, we can have a set represented by this blob and another set represented by this blob. And if this is set P and this is set Q, then this shaded area here is the intersection of P and Q. Okay, we also have something, oh no, I'll get to that in a moment. Let's talk about one other operation not talked about with sets. We know we have subsets, we have unions, we have intersections. Well, we also have something called a cross product of sets. Now this cross product of sets is not the same as cross product of three-dimensional vectors. It's not a vector, it's just another set. So, A cross B is a set of ordered pairs such that little a is from A, little b is from B, for all, I'll use that symbol, for all A in A, B in B. Putting it in, using these two sets, A and B, when A was a set, A, B, C, B the set, 1, 2, 3, the cross product set, A cross B, is the set containing the ordered pairs, A1, A2, A3, B1, B2, B3, and C1, C2, C3, okay. This set has 9 elements in it. How many elements in set A?
3.
How many elements in set B?
3.
So there are 3 times 3 elements in A cross B. The cross product set that we're most interested in mathematics is not the cross product of a couple of dinky finite sets like these, but a set of real numbers and the set of real numbers. Sometimes when we cross a set of real numbers with a set of real numbers, it gives us a set of ordered pairs, x, y, where every possible x, infinitely many, is paired with every possible y, infinitely many, and there are infinitely many ordered pairs. But the thing is, using this geometric representation, we have a one-to-one correspondence with all possible ordered pairs of real numbers, x and y, compared to all possible points on the coordinate plane or the Cartesian plane. And when you get to calculus 3, when you have r cross r cross r, 3 space. Often this is represented as bold-faced r squared. Okay. So, since we're dealing with numbers, let's talk about numbers. What is the simplest set of numbers that we commonly use? It's the natural numbers. Symbols for the natural numbers is aleph, null, and it is the set 1, 2, 3, 4, 5, etc. How many elements are in that set?
Infinity?
Infinitely many. Big set you can have, infinitely many. Not true. You can have larger infinities. And we'll get back to that in a moment. But, you know, with these we can add and subtract, we can add and multiply, and always end up back here. If we try to subtract or divide, we have to add more numbers to the set. In order to subtract, we have to add 0 and the negative integers. In order to divide, we have to add the rational numbers. So, how about the set of rational numbers? Well, I'm going to list them all, just like I listed all of these. In other words, you have to list it in a pattern that everybody agrees has them all in there. So, now I'll call this set Q for quotient. Q, the set of rational numbers, is, let's see, extend that a little more, because it's a much bigger set, I just say loosely. 0, 1, 2, 3, 4. Except I don't want to do that, because in order to list this, I want to be sure that we include all. So I'll say 0, 1, negative 1, 2, negative 2, 3, negative 3, 4, negative 4, and so on. What's the divisor in all these numbers? There's a divisor there. What is it?
1.
1. So what's the next divisor? 2. So we have 0 halves, 1 half, negative 1 half, 2 halves, negative 2 halves, 3 halves, negative 3 halves, 4 halves, negative 4 halves, and so on. I'll do another row. 0 thirds, 1 third, negative 1 third, 2 thirds, negative 2 thirds, 3 thirds, negative 3 thirds, 4 thirds, negative 4 thirds, and so on, and so on. Do you agree that every possible rational number is on that list? Not only is every possible rational number on that list, every possible rational number is listed infinitely many times. Because we have the number 1 and 2 halves and 3 thirds and 4 fourths and 5 fifths. Or you have the number 2 thirds, wherever 2 thirds went, 2 thirds and 4 sixths and 6 ninths and on and on and on. Infinitely many of each of those numbers. Well, in appearance, Q is much larger than aleph null. But the fact is, no, it's not. Because we say two sets are the same size if they can be put into a one-to-one correspondence with each other. Every counting number matches a rational number, and every rational number matches only one counting number. None left over. So, this is slip. Count with me. 1, 2, 3, you know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and so on. Is there a rational number that does not appear on this serpentine? They're all there. And you can get to any rational number in this list by counting up to it. 1, 2, 3, 4, 5, and so on. So that says the cardinality of, oh, I didn't mean to call this aleph. No, I'm ahead of myself. Just call this n the set of natural numbers. Boldface n, not aleph, but n. But the cardinality, the number of elements in this set, is equal to the number of elements in this set, and that is aleph null. Aleph null is the first trans finite number. Why did I say the first trans finite number? The first infinite number. If I said first, maybe there's a second, a third, fourth. How can that be? Well, it's pretty easy, because, let's go back here for a minute. I said I had a set A, and I had all the subsets of it. But if I consider the set of all subsets, then this is called the power set. And is denoted with an uppercase P, or exponent P. A power set is a set of all possible subsets of A. So even though the elements of this set are sets, there are more elements here than there are there. So, every set is smaller than its power set. Every set is smaller than its power set. So, if we start out with the empty set, its cardinality is 0. And the only empty set the empty set has is the empty set. What if I say, oh, I have the empty set whose cardinality is 0. Now look at subsets. Its only subset is the empty set. If I'm looking at the set of all possible subsets, and if I do a power set of this, I have the empty set, the set containing the empty set, contained by set. This has 2. So in essence, we can build up the counting numbers by looking at power sets or combinations of power sets to define numbers. But that gets a little too abstract. We'll just count on our fingers and toes and call it good. 1, 2, 3, 4, 5, etc. Okay, so we have transfinite numbers. So if I look at the power set of any set that has a cardinality of aleph null, it must be larger. Well, the next transfinite number is equal to the number of elements in the real numbers. And it's commonly abbreviated with the letter C. Not the speed of light as it is in physics, but the cardinality of the real numbers. Well, what are the real numbers? Well, the real numbers are all integers, whole numbers, negative integers, fractions, decimal fractions of the form that either terminate or repeat, and that leaves all the decimal values that do not terminate, nor do they repeat. Pretty easy to show that there is one. All we have to do is set up a pattern that we know how this goes forever, and we know that does not repeat. So I'm going to say 0.1, 0, 1, 0, 0, 1, 0, 0, 0, 1. What's the next 5 member string? Come on.
0, 0, 0, 0, 1.
That's it. 0, 0, 0, 0, 1. So you have the pattern. This does not repeat and doesn't terminate. It's in this case, an algebraic, because it can be defined algebraically. It is an algebraic irrational number. There are also what we call non-algebraic irrational numbers. A couple of examples of the non-algebraic irrational numbers is the number pi. You know, it's about 3.1415926535898, etc. Okay. Actually 97 and change, but it rounds to 98. Whew, that's out to about 15 places. And I think I mentioned last time that you need 15 significant digits to pin down your location using global positioning system to the nearest centimeter. So whether I'm standing here or there, GPS can't tell the difference. So if I move 2 centimeters, not quite an inch, now Big Brother in the sky knows I have moved. So beware Big Brother in the sky. Oh, I'm not too worried about it. Not yet. What's the one in the Terminator? Skynet? Okay, so what do we do with this? What we do with this is that we look at that cross product set that I was talking about, namely R cross R. So R cross R, quite frankly, is not very interesting. It only becomes interesting if we look at some of its subsets. So, because R cross R is the entire plane of this board, if you set up your axes someplace, or the entire expansion of this floor out to infinity. Now, realizing this floor is not really flat. Why isn't the floor flat? And the ceiling is larger than the floor? Have you thought about that? I take my earth, hello earth, and I build a room with vertical walls and a roof. I exaggerate here, but the floor is not flat. It is level, but it's not flat. The roof is not flat, but may be level, but you see that the roof or the ceiling is longer than the floor. Hopefully they measured this long enough that it just doesn't suddenly cave in on us. That'd be a little embarrassing. Well, we made it the same size as the floor. I'm sorry, that wasn't big enough. Of course, to be significantly different so that a GPS satellite could tell, you would have to have a rather large building. How long is the, 5001 building out at Tinker? Isn't that the name of the building, 5001 building at Tinker? How long is that building? At one time, that building out at Tinker Air Force Base, right there in Midwest City, America, had more interior volume than any other building in the world. Never knew that. It doesn't anymore. There are several buildings that have a greater volume. Now the building with the greatest volume, and I've been in it, it's one big building, is the shuttle assembly building, or the Saturn V assembly building, down at Cape Kennedy, where they launch rockets. That thing has a doorway that opens 500 feet high. You could take the Washington Monument and move it through that doorway and not have to chop anything off. That's a big deal. It doesn't look big because it's kind of sitting out there on the plain of eastern Florida, and there are no other objects close. That, yeah, okay, there's a building, and you get closer to it and closer, and you think, it's not the tallest building in the world by any means. It's not the longest building in the world by any means. But its interior volume is the largest in the world. So, back to our R cross R. It is not very interesting because we already know there's a one-to-one correspondence for every point in the plane, corresponds to an ordered pair. Every ordered pair corresponds to a point in the plane. So what we're interested in is subsets of that. Let's write an equation for one of those subsets. X squared plus y squared is equal to 1. Think back to your trigonometry, and one of the ways that we define trigonometric functions. What is the equation x squared plus y squared equals 1? Circle. It's a circle. What's its radius? 1. That is, someone's giving me the finger. I'm a finger, they may give me the deep finger. So it has a radius of 1, and where is its center? Center is at the origin. Because the standard equation for a circle is x minus h squared plus y minus k squared is equal to r squared, where hk is some point in the plane, and r is some radius, and we draw that radius and we have a nice circle. This is a particular circle, center of the origin, and, oh, by the way, I don't really have that one-to-one correspondence until I set up at least 2 coordinate values on each axis. Often we use 0 and 1, but now I have one-to-one correspondence with all points in the plane, one-to-one with all ordered pairs, and the ordered pairs that make this true is the unit circle. And we can define the trigonometric functions based upon that unit circle, and lots of things we can do with it. But this is a subset of a cross product set. So my first definition after defining a cross product set is to define a relation. Oh, by the way, B cross A is not the same as A cross B, even though it contains the same information, but the order is not the same, because its elements would be 1A, 2A, 3A, 1B, 2B, 3B, 1C, 2C, 3C, because the order would be reversed. So cross product is not commutative unless A is equal to B, as it is in the real numbers crossed with real numbers. Okay. A relation is a subset of a cross product set. Simple enough definition. So any scribble I put up here is a relation. This is a relation. Another relation, y equals x squared. Anybody recognize what this is from your Algebra 2 days or pre-calculus days? What is that? How many of you guys know this? Please tell me. Parabola. And it has to be what we say is the standard parabola, whose vertex is at the origin, and it goes through the point positive 1, 1 and negative 1, positive 1, and swoops upward, like so. That's also a relation. Relations are friends. But, to tell you the truth, we're kind of simple-minded. I mean, when you come to a fork in the road and you don't have a map, what do? You know, now in the old days we carried atlases with us that had all the states and all the major highways, and they have insets of the major cities, and you can kind of find your way around. But, you know, people don't have those things now. Have their cell phones, you know. They just go to Google Maps and it tells you how to get there. But, it died. Where am I? Came to a fork in the road, what do? So when we have a fork in the road, when we have more than one decision to make, we don't know what decision to make. If I tell you that x is 3/5 over there on that circle, what is y? X is 3/5. What is y?
3/5.
And a little more. What's a little more than 3/5?
6ths.
Oh, we stay with fifths. It works. I picked a number that works. 3/5 and 4/5. But also 3/5 and negative 4/5. They both work. That's indecisive. Most of us don't like being given two choices. I mean, a kid's worst nightmare is being, you know, when I was young, kid's worst nightmare was being given a nickel and turned loose in a candy shop. Which candy do you get? I mean, there's so many to choose from. On the other hand, if it's the only store in town and the only thing they have is licorice sticks, you buy the licorice stick and you're thrilled. But that's the only choice you have. Well, mathematics, I guess we're simple people. We like a single choice. So I want to restrict this definition of relation, pin it down to a single choice. And that is the thing that we deal with most mathematically, a function. A function is a relation. Oh, wait a minute. That means it's a subset of a cross product set. But I have to further refine it such that for each x there is a unique y. In other words, cross product set is a set of ordered pairs. A relation is a subset of that, but still a set of ordered pairs. A function is a subset of that, but still a set of ordered pairs. And usually we label the first element of the ordered pair as x and the second element of the ordered pair as y. We don't have to. If you're converting from degrees Celsius to degrees Fahrenheit, it makes sense to use C and F instead of x and y. But you know, if you're dealing with yucca plants, and what's the term for succulents? Starts with an X. Xerophytic? I think that's it. Spelled with an X. You have your X and Y. But if you're dealing with other things, you might want to use the letter that represents what you are thinking. Okay? Having said that, when you're using your calculator, inputting data sets in there, don't rename the columns L1, L2, L3, L4, list 1, list 2, list 3. Leave them like that, because if you rename them and forget the names, you can't access that. And so then you have to reset your calculator to get rid of those lists and stuff. So you might want to use L1 for pounds, L2 for tons, and L3 for kilograms. What's the difference between pounds and kilograms? Besides, one is about 2.2 times the other under 1 G. But pounds is actually a force and kilograms a mass. Okay. So of these two relations I have drawn over here, this circle is a relation, this parabola is a relation. Which one of those, or which both of those, or which none of those are relations? The answer is they're both relations. Well, let's go to the next question. Which of those, if any, are functions? Which one is function, which one is not? Parabola is a function. Circle is not. Because for any given x in the domain of the circle, with the exception of that point and that point, every other x value in the domain generates two y values. The value of y is not unique. But for the parabola, and for the parabola, the domain is all real numbers, and the range is all numbers greater than or equal to 0. But given any x, get up here high enough, and there's a single ordered pair that corresponds to that x and that y. And that single ordered pair is related that y is always equal to x squared for that function. So it's not that we won't deal with circles and ellipses and maybe some other shapes through the course, logarithm curves, exponential curves, and whatnot. But we prefer to deal with functions rather than relations which are not functions. I'm sure everybody in this room has some relations that they would rather not deal with. You know, I understand that. I have some of those. And according to some of those, I may be one of those too, you know. So, let's look at something. Let's look at a couple of functions. Simple functions. First function I'm going to say is y equals x minus 1. What kind of function is that? We have a name for that family of functions.
Linear.
They are linear functions. Now, this linear function happens to be a straight line. There are other linear functions like absolute value, which are not straight lines because it has a definite bend, instantaneous change of direction. Neat if you can do it, but you really can't do it. Can we graph this thing? Yeah. Think back to Algebra 1, back in 9th grade or 10th grade or last year, whenever you took it. What's the slope of this thing? 1. What is the y-intercept? -1. So if I begin at -1, up 1 over 1, because I have positive slope, and then connect the dots, then I have a graph of the line. Well, no, not quite. I'm missing a couple of things. What am I missing on that graph? What is that value?
091.
How do you know that? By looking at the picture. You don't. What's this line? It's the x-axis. How do you know that? You don't, because it's not labeled. So you need labels and scales. So this one I'll call X, this one I'll call Y. You can name them anything you want. I can call this Fred and Sarah. And also you need at least 2 points identified on each axis to pin down the scaling. Because sometimes we don't want to use the same uniform scale on both axes. We might have a vertical compression so that we can get more information in the picture. But here we will. This is negative 1, that's positive 1. If I call this 0, then I have 2 points labeled on the x-axis, I have 2 points labeled on the y-axis, I have the y-intercept identified, and the x-intercept identified. I have a good sketch of the graph y equals x minus 1. Okay. As we increase in complexity, first function we can talk about is constant function. Constant function is kind of boring. There are 2 times during the quadrennial that your TV behaves like a constant function. One is when it's not turned on. You look at the screen, what's the screen? Blank slate. Look at 5 minutes later, what's the screen? Blank slate. The reason I said quadrennial, what comes up every 4 years? Approaching November, election times. Turn channel 4, election coverage. Channel 9, election coverage. Channel 5, election coverage. Channel 12, election coverage. Channel 2486, election coverage. Oh, by the way, yes, as much as I don't like watching those things, I am registered, I vote regularly. I guarantee you that whoever I vote for, if that person wins, they will not fulfill their promises, so I can complain. If the person I don't vote for wins, certainly they will not fulfill my promises, so I can complain. But if you don't vote, and you're eligible to do so, you got to live with what they give you. You can't complain because you weren't in the process. So if you are of eligible age and eligible citizenship, register and vote. Then you can complain. There's a story of an old Russian immigrant came to the United States. I asked him a few questions. Said, "Well, how was your job over there?" "Oh, couldn't complain." "What did you have a nice house?" "Couldn't complain." "Well, how was the school for your kids?" "Couldn't complain." "Well, if there's nothing to complain about there, why did you come here?" He said, "Here I can complain." There's some truth to that, by the way, unfortunately. Having been to Russia, I enjoyed my visit there, but I was sure happy when the airplane lifted off the runway and was headed back east. How about west? East would have been a long way to go. Back west, toward Western Europe and the United States eventually. Okay, so there it is. So we have constant functions, next linear functions, then we have quadratic functions, then cubic functions. What's after cubic? Turns out it's quartic. And after quartic is quintic. And we kind of quit using those prefixes after that. And then we just say they're polynomial functions. A polynomial function looks something like this. F of x is equal to a polynomial. a0 plus a1x to the first plus a2x squared plus a sub 3x cubed plus and so on out to some nth degree a sub n x to the n. Where not all of the an's are equal to 0. If a sub n is not equal to 0, we say this is an nth degree polynomial. Nth degree polynomials are kind of interesting because they were the first functions we kind of got serious about. And back in the, trying to think when it was, very early 1500s, they actually solved the solution to a third degree polynomial. And shortly after that, they solved the equation for a fourth degree polynomial. You know, they're like the quadratic formula with a second degree polynomial, but third and fourth degree. Then, some years later, no one had figured out how to solve a fifth degree polynomial, a general fifth degree polynomial. Yes, there are lots of specific fifth degree polynomials that we can solve. As a matter of fact, if you looked at can't think of it right now. Whose laws? De Moivre's laws in physics. If I have x to the fifth equals 1, there are 5 solutions to that. One of them is 1. One of them is cosine 72 degrees plus I sine 72 degrees, and so on. There are 5 solutions around there, each 72 degrees apart. Okay. So some of them we can solve, but many we can't. And there's a 25-year-old mathematician by the name of Abel, A-B-E-L, umlaut over the A, because he was Swedish. Okay. And he proved that there was no general solution to a fifth degree polynomial. And he's so excited about that, he took it down to Germany, to the greatest mathematician in Germany at the time, Euler, Leonhard Euler, and he said, hey, look what I've done. And Euler, being the old wise guy that he was, you know, I'm smarter than everybody else type guy, he kind of looked at the 25-year-old and said, you know, this might be interesting, but you don't have the mathematical background or training to have done this. So, get out of my office. So dejectedly, he left his proofs there, caught the ferry back past Denmark up to, what's the capital of Sweden? Stockholm. I couldn't think of it this morning. You know, I got Oslo, Norway. Stockholm I couldn't think of. Back to Stockholm, and he caught a cold and flu and died shortly thereafter. About 10 years later, Euler was going through some of his stuff. He comes across this at the bottom of the pile. Oh, what's this? He looked through it and says, hey, the kid did it. He proved that there's no general solution for fifth degree polynomials, or any polynomial greater than that, by the way. We have exact solutions for constants, not very interesting, linear equations, quadratic equations, cubic equations, quartic equations. Each step gets a little more complex. But quintic and above, fifth degree and above, there's no general solution. Yes, for particular problems, there are specific solutions. In one of my graduate classes, number theory, Math 5333 down at the University of Oklahoma back in the day. By the way, for number theory, isn't it nice that the course number 5333 is a prime number? I thought that was nice. But anyway, one of the things I did was replicate the proof that Carl Friedrich Gauss did when he was 19 years old and published in a book at age 19. The proof of, or the solution of a particular 17th degree polynomial equation with 17 solutions that could be found by compass and straight edge. And it took me an hour and
20 minutes to demonstrate it to the class in a 50-minute class and nobody left, so it must have been interesting. I've forgotten all that now, but I still have it written down, like at home if I want to look it up. I have Gauss's book too. Unfortunately, it's not original. It's written in English, not German. But it's one I can read. I can't read the German anymore, if I ever could. Okay, so let's look at slightly more complex than polynomial functions. Let's go to rational functions. What is a rational function? What's a rational number? We had them all listed up here.
Ratio?
It's a ratio. So a rational number is a ratio of two integers. So a rational function is the ratio of two polynomials. So if I have one polynomial on top of another polynomial, bingo, rational functions. And rational functions get a little more interesting in some aspects than do just polynomials, because we have more to look at. So if I look at this one, y equals x squared minus 3x plus 2 divided by x minus 2. Okay. Back to the linear function. What is the domain of this linear function? All real numbers. The domain of any function, the default is all real numbers. Then we have some exceptions. Exception, division by 0. Exception, even roots of negative values. Okay. Looking over at this circle, if we pick an x out here and try to solve for y, we're looking at even roots of negative values. Can't do that. So we're restricted from -1 to +1. For the parabola, there's no such restriction. Negative infinity to infinity. For that line, there's no such restriction. Negative infinity to infinity. What's the restriction for that rational function up there?
2.
2 is a restriction. X cannot be 2. So the domain is all real numbers except 2. But let's graph this. Oh, by the way, when you have division by 0, how does that affect your curve? What happens at that point? You often get an asymptote. Well, I was sneaky. I don't think this one has an asymptote. How can it not have an asymptote? Well, let's do some ordered pairs.
Let me say y sub 1 and y sub 2 so we can differentiate. X, y sub 1, x, y sub 2.
I think I'll start at about -2,
-2, -1, 0, 1, 2. -2, -1, 0, 1, 2. Well, let's go more. 3, 4. 3, 4. Okay.
pick my x values. Plug in -2. -2 minus 1 is -3. -2. +4 plus 6. +10 plus 2, +12. Divide by -4 is -3. -1 minus 1 is -2. -1. 1 plus 3 is 4 plus 2 is 6. 6 divided by 3, -3 I should say. 6 divided by -3 is -2. Plug in 0.
-1.
Plug in 0. 2 over -2.
-1.
Plug in 1. 1 minus nothing. Plug in 1. 1 minus 3 plus 2 is 0 over -1 is 0. Plug in 2. 1. Plug in 2. 4 plus 2 is 6, minus 6 is 0. Divide by 0, 0 divided by 0 is not 0. 0 divided by 0 is still division by 0, it's undefined. Plug in 3. 3 minus 1 is 2. Plug in 4. 4 minus 1 is 3. Plug in 3 over here, we'll get 2. Plug in 4 over there, we get 3. So if I graph this thing, close. So I have my scales, my labels. Did remember my labels. That graph is exactly like this graph, with the exception of a single point. That's like an Oklahoma road after a spring thaw. Lots of chuck holes. Driving down the road, you think you know where you're going, and all of a sudden, ka-thunk. A disaster happened down on East I-40 many years ago, where a errant barge struck a bridge pier on the I-40 overpass, causing the span to fail. And this was old dark early. So people screaming down the highway at 70 miles an hour. Suddenly there's no road in front of them. I think 13 people were killed. One guy thought he got stopped enough, but the guy behind him didn't get stopped and bumped him over. That's a larger discontinuity. This is called a jump or a point discontinuity, or it may be a jump, because you can't get over here from over here unless you jump. Have to skip that point. Often, when we have division by 0, it does give us a vertical asymptote. In this case, it just gives us a missing point. I can modify y2. Let me do a y3. Y3 is equal to x squared minus 3x plus 2 over x minus 2, red, comma, x not equal to 2, and what is it at 2? Oh, 1, when x does equal 2. Now, y3 is identically equal to y1, because I filled in the missing point. But I could fill in that point anywhere that I want. Well, I better not put it that high. 7. 1, 2, 3. Oh, I'm sorry. 1, 2, 3, 4. I'm bringing it down some more. 5. 1, 2, 3, 4, 5. Okay. Now, what's the domain of this function? All real numbers. If you're driving along this road, where does it look like you're going to go? It looks like you're going to that point. It doesn't matter that you're going there. It only looks like you're going to that point. Okay. Well, that's kind of the idea of a limit. Let's do some sketching back on this first board again. First time I taught engineering mathematics, I was in a very small room. There were only 10 students. I had this much board. Can you imagine doing engineering mathematics with that much board? I went up to the talk chair and said, hey, Look at the course number, look at the text. Do you expect me to do this on this much? Come on. Sorry, I gotta move to a larger one. That was insane. Calculus is not quite as board consuming on a single problem as engineering mathematics, but you see I'm filling up the panels on a regular basis. So, if I have a circle, there are several things that we identify with relation to a circle. One, we identify the center. Center is not part of the circle, but it's a defining point of the circle, because in order to get the circle, you need to define the center and the radius. But any segment from that center to the circle is called what? Come on, what is that? The radius. On the other hand, if I extend that radius in the other direction just as far, then we no longer call it a radius. What do we call it? Diameter. Diameter. Okay. Well, if I have a segment that goes from one side of the circle to the other side of the circle, but not through the center, we have a name for it too. What do you call that?
Second. Second.
It's not a secant, but it's close. When you're playing the guitar, what do you try to play in?
Chord.
Chord. This is a chord. C-H-O-R-D, chord. The same CH as in chemistry. Not the same CH as in church. Or maybe it is, there's a chord. But if you extend the chord, if you extend the chord beyond the circle, then sure enough, we call it a secant. And in the special case, where this just comes sweeping by, touching at a single point, what line do we call that? Tangent. If I have a quarter of the unit circle here, and I have some angle theta here, then I have several segments related to this segment. This segment's the sine, this segment's the cosine. If I extend this line, then that's the tangent. And all the way out, that's the cotangent. And from, I need to know this quote. The reciprocal of the sine is the cosecant. Now, where is it? They're all up here. There that is. I've lost my secant and cosecant. They're in here someplace. I have to look that up. Anyway, all 6 of the trigonometric functions can be shown on a unit circle by segments. Sine, cosine, tangent, cotangent, and secant and cosecant are somehow involved in there. I know, missed it. Out to there is the secant, and out to here is the cosecant. I knew they were there someplace. I just lost them for a while. So, those 2 things, and actually 3, chord, secant, tangent, apply to any curve. So if I have some curve here, and I pick a couple points on that curve, and draw a chord, extend that chord, then, sure enough, what we have is a secant line. Secant. Okay. Now, since the secant is a line, I can define the slope of that line. If this is x1 comma f of x1, and this is x2 comma f of x2, then the slope of that secant line is a change in y, f of x2 minus f of x1, over the change in x, x2 minus x1, in the same order. I get the same result if I did f of x1 minus f of x2 over x1 minus x2, because both of them would change signs, so the net result would be there's no change. So that's the slope of the secant line. We use that to define the slope of any line. Okay. So, but what I want to look at is not the slope of the secant line, but perhaps the slope of the tangent line. At some point, there's a line that is tangent to the curve at that point. I want to find that slope. But what information do you have to pin down a line? You need two pieces of information. You either need 2 points, defines a unique line, or a point in some direction, which defines a line. But there, all I have is a single point. So I have to find some way to come up with a slope, except to come up with a slope, you need 2 points. So I have a bit of a quandary here. Let's go back to this pretty picture. Limit, abbreviated LIM, as x approaches the value of 2 of y sub 2 is 1. Okay. The limit is that value, intuitively, that looks like you're going to. There's an engineer and a mathematician, they're both interested in the same young lady. And she was having trouble deciding between the two, but she was recently bright herself. So she said, I tell you what, both you stand on that wall and I'll stand on the other wall. Each time I clap my hands, you can move half the distance to me. So the first time they move halfway across the room. The next time they move a quarter of the way, and the next time an eighth, and so on. And the engineer, being the practical one in there, says, oh man, I'll never get there. But the mathematician says, oh, I can get as close as practically necessary. So, if I add 1 plus a half plus a fourth plus an eighth plus a 16th plus a 32nd plus a 64th, what is the eventual sum? Well, I started with 1, so it's 1 plus 1 is 2. So if I get close and kind of see where it's going, then I can lay claim as to a value. So instead of calling it x1 and x2, let's call the point of interest and call any other point on the curve x f of x. I'm interested in the slope of the tangent line. Using this concept over here, I can write the equation of that secant line, or the slope of the secant line. The slope of the secant line is f of x minus f at a divided by x minus a. Slope of the secant line. If I look at the limit as x approaches a, if I can find that value, then my claim is I will have the slope of the tangent line. Oh, by the way, a tangent line here may in fact be a secant line someplace else. I don't care what it does out here. I'm only interested in what is it doing in what we call a neighborhood. Neighborhood's kind of interesting. It's as large or as small as it needs to be. Has to be small enough not to include any of those points. So, let's do one the hard way first, not knowing that we talked about this all day. I want to look at your basic parabola once again. F of x equals x squared. And I want to find the slope of the tangent line at the point 2, 4. Because 2, 4 is an ordered pair on the curve, right? Okay. Well, sketching this, we have the parabola climbed like this, and at 2, we go up 4. So I'm interested in this slope up here, whatever it might be. Okay. Well, one of the things I notice is, in the case of a parabola, it's very clear that that tangent line intersects that parabola at only a single point. Here, more generally, it's not necessarily true. But with a parabola, it's pretty clear that that's true, because even though this leans out a little, it never leans out. It gets steeper and steeper vertically, whereas the tangent line doesn't get steeper and steeper vertically, so they'll never intersect, except at the one point where it just osculates that point. Just touches. So, this is a line that contains that point. We can write the equation of a line containing a point, but we don't know the slope. Yeah, we can still write the equation. Y equals the slope times x minus x1 plus y1. Isn't that the equation of a line? Through the point 2, 4 with an arbitrary slope. This covers all possible lines through that point except for vertical. If m is 0, we have the horizontal line. If m is 1, we're up there. If m is 2, we're up there. With m equals some other positive number, we hit the tangent. If m is negative, we're sloping in the other direction. If m is infinity, we get the vertical line. Or negative infinity, we get the vertical line. But those aren't real numbers, so that line's not included. I know the equation of the ellipse, y equals x squared. I know the equation of the line, y equals m times x minus 2 plus 4. So I have a system of equations, two unknowns, but they're not both linear, so when they're not both linear, what is the method of solution that's usually used to solve that? Substitution. In other words, we take this y, and we put it in for this y. And we see if we can solve that equation. That is, y equals y. Now I'm reduced to one equation and one unknown. One equation, one unknown, and it's quadratic. And so if it's quadratic, what can I use to always solve a quadratic formula?
Quadratic equation? Or formula?
Use quadratic. What can I use to solve a quadratic equation? Answer is quadratic formula. So we can apply the quadratic formula. That means I got to get everything on one side. I rewrite this as x squared minus mx plus 2m plus 4. Okay. And we remember, given a quadratic equation, oh, by the way, equals 0. Given the quadratic equation ax squared plus bx plus c equals 0, then x is the opposite of b plus or minus square root b squared minus 4ac all over 2 times a. Whew. And this value in here, called the discriminant, talks about the nature of the roots. If the value inside is positive, we get 2 real unequal zeros. If the value inside is negative, we get 2 complex conjugate zeros. And if the value inside is equal to 0, how many solutions do we get? Well, second degree, we always get 2. But the answer is, they're both the same. So effectively, we get one solution if b squared minus 4ac is equal to 0. So in this equation up here, what is A? What is B? What is C? So I can write the solution. X equals minus b plus or minus square root of b squared minus 4 times a times c all divided by 2 times a. Oh, I missed that. Time out. Four times a times c four times 2. 4 times this is 8. 4 times this is 16. Okay, finally have it all in here. Over 2 times, okay, there we go. So there's my general solution for x, given any m. But I want the solution for x that only has a unique solution, a single solution. So I'm insisting that m squared minus 8m minus 16 is equal to 0. I'm taking the discriminant and insisting that this value equals 0. Well, this is a perfect square trinomial. It factors. M minus 4 times m minus 4 equals 0. That is right.
This should be negative 4.
Oh, this should be plus 16. When I brought this over, it's plus. When I bring this over, it's minus. I knew I had something didn't look right. Okay. So now when I have minus 4 times m times, or 4 times a times c, we get minus 4 times this, negative 8, minus 4 times this is plus 16. Okay. Whew. So this factor is m minus 4 times m minus 4. M equals 4. Oh yeah, that's right. So it says that if m is equal to 4, we have a single point of intersection. So I found the slope of the tangent line. That is painful. Oh, by the way, I demonstrated while doing this that I can make arithmetic and sign errors very quickly. You know, I work problems very quickly. Sometimes I get the right result. So when you catch my mistake, thank you, please point it out so that we can get it corrected so that not everybody leaves with incorrect notes. And at the end of the class, I always erase the board for 2 reasons. One is a courtesy to the next instructor that may be coming in. And 2, so the next instructor coming in doesn't see my mistakes. So it's up to you to catch them. Don't go away and say, I think you missed that. Bring it to my attention before you leave so that we can clarify it. Worst case scenario, I'm right and you're wrong. The world does not come to an end. Thank you for clarifying it in your mind. Best case scenario for you is you're right, I'm wrong, and you've been elevated among your peers. You suddenly found 23 study partners that all want to work with you. By the way, forming study groups is a good idea because you can find each other's sign errors. Okay, so that's kind of a pain. And if it were a more complicated equation, like a cubic equation, then the solution becomes more complex, more difficult to try to solve. So, let's see if we can solve that one this way. We still have f of x equals x squared. We're still looking at the point 2, 4. That is, f of 2 is equal to 4. I want to look at the slope of the secant line, f of x minus f of 2 divided by x minus 2. Let's put that information in. X squared minus 4, f of x is x squared, f of 2 is 4 over x minus 2. This behaves very much like that first rational function I had on the board. I want to look at the limit as x approaches 2. By direct substitution, we have 0 over 0. Doesn't help. But if I factor the numerator, x minus 2 times x plus 2 over x minus 2, I have a grammatical error. Limit x approaches 2. Because I've not drawn the limit yet, I'm still looking for it. X minus 2 times x plus 2 over x minus 2. So everywhere this is identically equal to this. Both are undefined at x equals 2. But for all values not equal to 2, those divide out. So now this behaves everywhere like that, except it has a single missing point that we're excluding by this division. By doing that division, we tossed out the missing point. So I wouldn't say, oh, let x equal 2. If I put 2 right there, what do we have? What's 2 plus 2? So when we draw our conclusion that that result is 4, we're done. Let's do one just slightly more complex. Well, let's actually do a couple more. First, I'll still do a quadratic. Let's say that f of x equals 2x squared minus 3x plus 5. And let's say at 3, 18 minus 9 is 9 plus 5 is 14. What's the slope of 314? So, I want f of x minus f of 3 over x minus 3. I want to look at the limit as x approaches 3. Well, let's do a little substitution. This is the limit as x approaches 3 of 2x squared minus 3x plus 5, subtract 14, divided by x minus 3. Let's do the arithmetic in the numerator. We're looking for the limit as x approaches 3 of 2x squared minus 3x minus 9 over x minus 3. Well, algebraically, this is almost as nice as the one we just did because it does factor. X minus 3 times 2x plus 3. How about x minus 3, 2x plus 3? Yeah, plus 3. Got it. Or x minus 3. Check my factoring. First term, 2x squared. Middle term, 3x minus 6x is negative 3x. Last term, negative 9. Good to go. That's the factoring. This is still the limit as x approaches 3. Again, everywhere that x is not equal to 3, this nicely divides out. So at x equals 3, that has a slope of 9. Well, let's do one that's next step up, cubic. And let's pick 0.28. What's the slope of that thing at 2.8? Well, same game. the slope is, and right now, rather than call it slope, I'm going to call it the instantaneous rate of change, because I'm going to first define the average rate of change is f of x minus f of a over x minus a. The average rate of change near or at, well, between a f of a and x f of x. Okay, average rate of change. Now, if I find, let me abbreviate this, a rock. Now, if I look at the limit of this, the limit of the average rate of change as x approaches its value a, we call that the instantaneous rate of change. IROC. That's not the International Race of Champions, but it's instantaneous rate of change. Okay. Well, let's do it for that function at the point 2, 8. So what I want is the instantaneous rate of change, that is the slope of this tangent line at, that is f of x minus f at 2 over x minus 2. In particular, that is x cubed minus 8 over x minus 2. Oop. Man, limit as x approaches 2. Limit as x approaches 2. X cubed minus 8, a difference of cubes factors. Side note, x cubed minus y cubed is x minus y times x squared plus xy plus y squared. Okay. So this factors limit as x approaches 2 of x minus 2 times x squared plus 2x plus 4 closed divided by x minus 2. Just checking my factoring, x times x squared is x cubed, x times 2x minus 2 times x squared is 0, x times 4 minus 2 times 2x is also negative 4x, adds out, and the constant negative 2 times 4 is negative 8. So that's the proper factorization. And everywhere that x is not 2, this divides out nicely. So this whole average rate of change behaves like that for all values of x not equal to 2, but specifically at 2 becomes the instantaneous rate of change, and is 2 squared is 4, plus 2 times 2 is 4, plus 4 turns out to be 12. So the instantaneous rate of change on the cubic comes flying up here, flattens out, goes through there, climbs steeply at 2, 8. At slope is 12. So we have a way to find the instantaneous rate of change. Now, quite frankly, this algebraic way is not the simplest way to do it. What we're going to be doing very soon is finding a simpler way to do it and developing a set of rules. Just like the ABCs, we'll have a set of rules that tell us just by inspection that the instantaneous rate of change of this at any point is 3 times x squared, just by looking. And by looking at this, I know the instantaneous rate of change at any point is 4x minus 3. Guaranteed. But before we can get to there, we have to understand the process. So right now, we're doing the algebraic process to find the average rate of change, then take its limit to find the instantaneous rate of change. Or we're talking about change in a function. One, we can just have change in a function, f of x2 minus f of x1. Okay? Today my IQ is 185. I may be exaggerating a little. But because of my age, tomorrow my IQ will be 184. So my change is negative. Okay. You, on the other hand, because you're in calculus, I'm guessing that the low end of the IQ in this group is 115. The high end, I don't know, 140. Who knows? I don't know. Anybody make 36 on their ACT? I had a summer intern one time that had a 36 on his ACT. Me and this aerospace engineer, PhD, worked very hard coming up with problems for him to solve during his eight-week internship. We figured this would consume his whole 8 weeks, and if he wanted to stay longer, it'd take him longer. In the first week, he had a flow chart depicting how the solution must work out. By the end of the second week, he had it done. This kid's smart. Now he works full-time for the FAA. I get $2, relatively speaking. He entered University of Oklahoma as a junior because his ACT was 36 out of 36. Bright kid. If I were still working in the same office I worked in when I retired, his dad would now be my boss. But when I was working there, his dad was just one of my peers. His dad's pretty bright too, but not as smart as his son. And I don't know if I'm as smart as my sons. But I am better at math than they are. But one is a science person. Hard to find something I know in science that he doesn't know. And the other covers all the other subjects. I mean, his major was in social studies, but I mean, he even subbed in home ec one time, years ago. So, anyway, so we have a change in function, fx2 minus fx1. And we have this average rate of change that we've talked about. And if I made a graph of time versus position, then, whoop, yeah, he's backing up there. Backing up here. Then he's going forward. The slope on this curve is distance divided by time. Go back to the inside front cover of your 8th grade math book, and there's some formulas. And one of them says speed is equal to distance divided by time. It's a rate of change. Now, here is distance and time. But mathematically, it's the same as any change in y over any change in x. The limit as the denominator approaches 0 gives us the instantaneous rate of change. Supposedly that's what your speedometer is reading out as you buzz down the highway. But as you're accelerating, usually the speedometer is lagging behind your true speed. And when you're braking, gingerly, usually the speedometer is, again, lagging behind the reduction in speed. It's not the fall that gets you. It's a sudden deceleration at the end of the fall that percentage. I rode a unicycle for years, was halfway decent at it. I don't anymore, because my reaction time is not what it used to be. And I'm heavier, and my bones are not as strong. Ding, 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 it's time to give the unicycle to one of my granddaughters and let her learn. So, okay. There's another change that we're used more in business calculus than in math calculus, and that's the percent change. And the percent change is f of x2 minus f of x1 divided by f of x1 times 100%. Percent change. If you're interested in percent change, if you're making an investment, invested $10,000, 2 weeks later is $20,000, you have a 200% change. 200% change. On the other hand, if I invest $10,000, in 2 weeks it's worth $1,000, I have a negative 90% change. But, percent change. Okay. What we've been talking about